In this work, we present a new sampling strategy for the lower body of legs platforms to improve end-post planning success rate and decrease planning duration times on environments with inclined terrain and obstacles. We designed a testbed of interchangeable inclined support regions for our experimental validation. In the two experiments being shown, the testbed and the target are the same. However, on the right-hand side, an obstacle is present, and therefore the automated pipeline plans a different grasping configuration and stance location to avoid that obstacle. In this next experiment, the testbed layout has been reconfigured to include more challenging supports with 15 degrees inclination, as opposed to the previous experiments on which the testbed was comprised of 10-degree slopes. Once again, given a bimanual grasping target, our method accommodates for any kind of terrain within the robot capabilities, and plans a whole-body pre-grasp configuration. Our planning pipeline can be portrayed as a self-contained tool that outputs a whole-body configuration when a pose for both left and right hands are queried. In more detail, the pipeline consists of 4 main stages. At the time of a request, the first stage filters the datasets and recombines them to produce a list of whole-body candidates, sorted according to the cost function f. Later, the candidates are examined until a feasible solution is found or the list is exhausted. During offline sampling, we approximate the upper body center of mass position by adding a lumped point mass to the model of the lower body. This allows us to estimate the robustness of the static equilibrium of a lower body configuration ahead of online recombination. Using the robustness measure as a rejection criteria during sampling enables us to exclude unbalanced leg configurations, increasing the quality of the stored samples. In order to evaluate the improvements of our proposal, we conceived 2 benchmarking environments on a testbed with multiple support regions with different inclinations. Results show we can get a success rate of above 80% on a highly constrained environment using a lower body dataset with only 50,000 samples, and almost 99% on obstacle-free environments. Furthermore, average and standard deviation of rejected candidates until a solution is found is orders of magnitudes below the actual total amount of candidate configurations, thus showing the cost function for sorting candidates is reliable and adequate.